Well, I would suggest two things. Elizabeth Peterson is ready to go. We could have Elizabeth go now while we're, and then swap, or we could.
Elizabeth's presentation is 10 minutes, right?
Correct.
Yeah. So we could, I was just writing to Keynote, we could invite the program and have the talks now, the short talks.
Okay, I'm fine with it. Okay, so let me introduce, just a minute. I just don't want to change the program so much that, so Yuan Ping is not there, correct?
Oh, I thought he was there. Huh?
So the 4 short talks are by Yuan Ping, Ab-initio Ultrafast spin dynamics in solids, Elizabeth Peterson, Amisi Safari, and Ridwan Agbaoye. I'm sorry if I don't pronounce the name correctly. Agbaoye.
Yes.
So, Agbaoye.
You tried.
I'm sorry, you tell me.
No, you tried.
All the 4, are all of them there? So can we go with the 4 short talks right now?
I think Safari is here. All right. In any case, he sent us also, yeah, Safari is here.
Yuan Ping?
He also sent us a video. Yeah.
Yuan Ping?
He's not here, but Elizabeth is here and ready to go.
Okay.
So I think we can start with Elizabeth and then move on to Safari and then Ridwan.
All right.
And
okay.
After Ridwan, we can, yeah.
Okay. All right. So let's start. So without further delay, welcome, Elizabeth. I don't have the title of your talk, but you are welcome to start your presentation.
Great. All right. Am I in the correct mode?
Yes, Elizabeth, it looks good.
Everything's fine. Yes.
Perfect. All right. Well, thank you so much for the invitation to speak today. And I'm Elizabeth Peterson from UC Berkeley and Lawrence Berkeley National Lab. And today I'm going to talk about exchange-induced valley splitting in transition metal dichalcogenide monolayers. Let's see. So transition metal dichalcogenides are a class of layered semiconducting materials that can be exfoliated down to the monolayer limit. And in the monolayer limit, they lose their inversion symmetry. And one of the consequences of this is that the K and K prime point in the hexagonal Brillouin zone remain energetically degenerate, but they lose their equivalence. And they're still connected by time reversal symmetry, which gives rise to spin valley coupling, where in the spin orbit split valence band, you have upspin in the K topmost valence band and downspin in the K prime topmost valence band. And one of the consequences of this is that you can selectively excite one or the other of the valleys with circularly polarized light of opposite polarizations. What I'm interested in is what happens when we break this time reversal symmetry, which allows us to isolate the band gap in one or the other of these valleys, and we can detect which valley polarization we're in using circularly polarized light. And this is potentially a binary quantity that could be used in valleytronics technology for beyond Moore's law information storage technology. This phenomenon has been observed by applying magnetic fields to transition metal dichalcogenides and can produce valley splittings on the order of 0.1 to 0.2 millielectron volts per Tesla, which is quite small. Magnetic substrates, however, are capable of producing valley splittings an order of magnitude larger than applied magnetic fields, on the order of 1 to 10 millielectron volts. And this begs the question, what is so special about magnetic substrates? Why are they so much more effective than magnetic fields? How can we know which magnetic substrates will maximize valley splitting? And what this comes down to is that at this point, general design principles for optimal substrates are a piece of information that's really lacking in the community. So what I've done is performed a bit of a Gedanken experiment where I take a monolayer TMD and I take an iron atom and place it at arbitrary locations above the TMD. And I consider both 100% coverage to see what's the absolute maximum valley splitting that we could achieve, where coverage refers to how many iron atoms there are per transition metal, tungsten or molybdenum. And I look at 33% coverage, which is a bit more realistic for an actual substrate. And I'm performing these calculations using VASP with PBE with Grima D3 van der Waals corrections and spin orbit coupling. Okay, so going back to the band structure of the transition metal dichalcogenide, you can see that at K and K prime, the spin orbit split valence bands are degenerate with opposite spin character. When I introduce the iron atom, you see that something clearly changes at K and K prime, and they are no longer energetically degenerate. And this is good because it means that we can track what's happening to these eigenvalues to learn something about the valley splitting at different coverages and alignments. And before I go on, I want to make sure I define these quantities I'm going to refer to clearly. So valley splitting is the difference between the dipole allowed band gap at K prime and at K. And this is the physical observable. This is what's observed in photoluminescence spectroscopy or reflectance spectroscopy. But what I'm going to talk about is valence band splitting, which is the difference between the topmost valence band at K and at K prime. And in my studies, these two quantities typically vary by no more than about 5%. And I'm going to use the valence band splitting because that's what's relevant to this model that I'm going to develop going forward. So we begin with proximity effects. So if I place the iron atom directly above the transition metal and move it up and down, what I observe is an exponential decay in the valence band splitting, where tungsten diselenide has larger valence band splitting than molybdenum disulfide. If we zoom in on 4.4 angstroms, which has been shown in prior literature to be the stable separation between surface europium atoms and WSE2 in a europium 111 plus WSE2 heterostructure. At 100% coverage, WSE2 can have a valence band splitting up to 150 millielectron volts, which is enormous. It's an order of magnitude larger than the largest valence bands or valley splitting that's been observed. And if we go to 33%, which is maybe a little bit more realistic, we're still looking at about 30 millielectron volts, which is larger also than anything that's been observed. And I think that's partly because the lattice parameter alignment of all of the substrates that have been studied so far isn't that great. And you can understand why that's a problem if you look at what happens when you fix the position of the iron atom above the surface and move it to the left and right. You observe this sinusoidal variation in the valence band splitting, where when it's midway between transition metals, you're maybe 20 to 30% smaller valence band splitting than when you're directly above the transition metal. And what this tells us is that orbital overlap must be a driving force behind the valence band splitting, that the proximity is really important and orbital overlap is an obvious factor in what's driving this phenomenon. So the next knob I can turn is I can change the out-of-plane magnetic moment of the iron atom. And so I tried rotating the magnetic moment from being fully out of plane to being in plane. And what I see is a linear relationship between the out-of-plane magnetic moment of the iron atom and the valence band splitting. And this immediately makes you think of a Zeeman effect, that there is clearly something Zeeman-like about this phenomenon. I can also change the atom from iron to chromium, which has a larger calculated magnetic moment and indeed has a larger valence band splitting. And it actually scales just about linearly with the increase in the magnetic moment. Zinc is a filled D shell non-magnetic material. So I tried zinc as well, and I got no valence band splitting, which intuitively makes sense, but is important because it means that it's not just about the orbital overlap. The out-of-plane magnetic moment is a big driver of the valence band splitting. And so I wanted to develop a model that could describe this phenomenon. In the literature, typically this is described as a Zeeman-like phenomenon, which it certainly is to some extent, but the orbital overlap piece of it isn't captured very well by existing models in the literature. So what I've done is I've started with a model Hamiltonian where I have the unperturbed transition metal dichalcogenide dispersion. I have the unperturbed iron atom, and I introduced the mixing term. And there's a whole cornucopia of terms that you could develop here. But I pick one that's not going to be necessarily the same at K and K prime, a sort of effective exchange model Hamiltonian term. And I treat this as a perturbation. And when I do that, I can go to second order in the eigenvalues and look at how they're affected by this perturbation. And what I find is to first order, I get a quantity that's sort of equal and opposite, where this capital MSFE is the spin magnetic quantum number of the iron atom. And I get something that's asymmetric at second order. And I make a number of assumptions. First of all, I assume that the exchange parameter at K and K prime are the same, which makes sense if you consider hydrogenic orbitals and you consider the fact that at K and K prime, the topmost valence band orbitals are dxy and dx squared minus y squared orbitals. I also assume that this J goes as an exponential decay times a polynomial, which makes sense again if you consider hydrogenic orbitals and their overlap. And when I put this all together and take the difference between the valence band eigenvalue at K and K prime, and I factor in that you can rotate the magnetic moment of the iron atom, what I get is something that is linear in the Z component of the magnetic moment of the iron atom, but also has this quadratic relationship in the orbital overlap exchange parameter, which captures both this Zeeman-like effect, but also this orbital overlap effect. And so I tried fitting my data to this model, looking just at the valence band splitting when I vary the Z position when I'm directly above the transition metal. And what I find is A, I can get very good fits to this data, and B, when I plot the exchange parameter J, and we zoom in on 4.4 angstroms again, I get exchange parameters that are on the order of tens of millielectron volts, which is the order of magnitude that I would have expected. And this is encouraging because it means that this actually, you can capture this and you get intuitive results for your exchange, and you get data that accounts for the orbital overlap and the out-of-plane magnetic moment. So to summarize that, these general design principles that I've developed, first, vertical proximity is critical because this is an exponential decay. And you can mitigate this by using a magnetic ion to terminate your substrate. The lateral alignment has a sinusoidal variation, and you can mitigate this with lattice parameter matching, which is something that the existing heterostructures that have been explored, like europium sulfide and chromium triiodide, don't have valley splittings as large as what I'm observing. The out-of-plane magnetic moment is a linear decay, and the larger your magnetic moment, the larger your valley splitting is going to be. And finally, the radius of the transition metal dichalcogenide is important. If you have a larger TM or transition metal like tungsten, you're going to have more orbital overlap and you're going to maximize this exchange parameter. And all of this can be explained and understood using this effective exchange model Hamiltonian perturbatively. And with that, I'd like to thank everyone who helped me make this possible, and thank you for your attention.
Thank you, Elizabeth. We will go into, should we have a quick question now, or?
We do, and we have a question from Michelle Cote.
Okay.
In the chat.
Yes, can you hear me?
Yep.
Yep.
I was just wondering, can you use total energy in your calculation to determine exactly the location of the iron atoms above the planes? Like,
you mean like the most stable location?
Yes.
Okay, so in this system, if I look at that, the iron atom wants to be completely adsorbed on the surface. It doesn't want to be 4 angstroms above the surface. So I can't really determine what the most stable substrate separation would be, because that's a very different sort of heterostructure than just having these iron atoms directly above the surface. So the answer is no, I can't access what would, in a realistic substrate, be the stable separation using this model.
Okay, thank you.
Yeah.
Elizabeth, I have a quick question.
Mm-hmm.
When you have these add atoms, I didn't see you talking about shifting the Fermi level of the transition metal dichalcogenide.
Oh yeah, it does move a lot. I've got some plots of the valence band eigenvalues, and the Fermi level does move a lot.
Yes,
and
that's
so,
what I was wondering.
yeah, it does move around. And so when I was looking at the eigenvalues, what I did was I also did electrostatic potential calculations to determine the absolute vacuum position. So these are corrected for the shifts in the Fermi level. But yeah, it does change.
Okay, so I think we should move on to the next speaker, and we'll go back to. Thank you, Elizabeth.
Yeah, thank you guys so much for the invitation.
Sure. The next speaker.
So I'm sorry, Renata. So we will then, Alexandru, come back to your question. We do have one more question. Would that be all right?
Oh, okay.
Yes.
Okay. Sure. The next, Alexandru. Do you want to ask the questions I have here in the chat?
Yeah. So
okay, go ahead.
The question was just if you've tried making a Wanya model to evaluate, the hopping between the atom that you move and the material as a function of distance.
At this point, no, but that's something I would like to look into. It's on the to-do list.
Thanks.
Okay, thank you, Elizabeth. Amy, I believe Amisi Safari is online, right?
Yes.
Amisi, are you ready to give your presentation? Amisi? I have a problem here as well.
Okay. Hello, Amy.
Actually, for Amisi, we have a recording of the presentation.
Okay. So it looks like we have a recording, Amy.
Yes, that's correct.
Perhaps
hello?
I'm going to open the breakout rooms, and Sinead and maybe Sara, if you want to keep testing in the speaker ready room, would that work?
Okay, I can go to the break room and do the test.
Okay. And then yes, let me play Amisi's presentation.
Okay.
Let me cue that up.
Or if he's there and he can speak, Safari.
Oops.
Safari, are you there?
Hello, Mululu. I'm there, but my connection, I don't know if it's me.
Oh, okay. Yeah,
Amy.
so let's try so that Amy can play your video.
Yep.
Yeah. Thank you.
اوكي هو قاعد في الديسكتوب صح؟ الديسكتوب بتاعك
Amy?
Yes,
Okay.
can you see the presentation?
Yes, very good. Great.
Well, if you play it, can we hear?
Yeah.
You should raise the volume, please.
Yeah, the volume is very low.
Oh, okay. Then I'm going to send the link to you, Renata, in chat.
Yeah.
Can you play it?
Yeah.
From your maybe?
Okay, good. Yeah.
Yeah.
Are you seeing the presentation? Should I share screen?
Yes, I'm going to stop my share.
Okay.
Okay. And then Renata, can you share your screen?
This is amazing technology.
Okay, Amy, can I test mine?
Let me set up my screen here, full mode, if I can.
Let's go. I would propose we play Safari Amisi's presentation, and then Sara, we will come back to you.
لحظة بشنات ولا شنو؟ كم حاجة بشنات شنات الفيديو كلمة حاجة
The volume is still very low.
مش بالحاجة اللي أنت خشيت بها هيك تفهم.
So Renata, I think that it's also quite low, the volume. Renata?
Yeah, there is nothing I can do. I don't know how to change the volume here.
Okay, let me try mine. Is this better?
I am hearing pretty well.
Okay, maybe Renata, let's see if mine will work a bit better then. Let's try again. All right.
Sorry, can we just play the video and then Safari, you just talk about it? Safari, is this okay? We play the video and you just talk about it.
Could you say that again, Omu?
I said Safari could talk about the video. Like we play the video and he just tells us what is happening.
Okay, so I'll play the video from here. And can everyone see the video and the slides?
Yeah, we can see it.
Great. And
so Safari,
are you there? Okay, I've muted the video.
Yeah, so Safari.
Safari, we can't hear you.
Sorry, let me ask you a question. Amy, when you play it, can you hear on your laptop?
Yes, I can. And I have the suggestion from Yo Yamamoto, when you share a screen, share computer audio also needs to be checked.
Yeah, that's what I wanted to say.
That's what I didn't know how to do it.
Okay, let's see.
Connection is back. I don't know if you.
Safari?
Do you hear me?
Yes.
Yeah, we hear you.
Yes.
But let's learn how to share the computer audio too. No?
Oh.
So Renata, or would you like me to share?
If you want to start his video, please go ahead.
Okay, I'm going to start the video.
Yeah, but do you know how to share the computer audio?
I am clicking the options, but okay.
Option will appear when you press the screen sharing at first. It's in the bottom of the screen sharing screen.
Okay.
Okay. Oh, there we go. Okay, thank you.
Okay.
All right, now let's try one more time.
So, properties of the different phases of strontium hafnium compared to study of strontium zirconium oxide.
Yeah.
What was our working?
Okay, I want to restart it. I would like to start it again. Thank you.
Good.
Okay, thank you so much.
Thank you.
So we should say thanks to
I present
who are the geniuses that helped us. Yo Yamamoto, thank you.
Okay, I'll start now.
Who told us, yeah.
First, the principal study of structural and vibrational properties of two perovskite compounds, strontium hafnium compared to strontium zirconium oxide. My name is Amisi Safari. I'm from Bukavu in Democratic Republic of the Congo. we systematically present a first principal study of the structural, dielectric, and dynamic properties of the different phases of strontium hafnium compared to study of strontium zirconium oxide. What was our working method? First, we relax each compound in the high symmetry cubic structure. In this phase, we calculate the cubic lattice parameters, the phonons, the bond effective charge, and the phonon curves obtained, as well as the analytical values of the associated frequencies and the eigenvectors, allow us to condense one by one each observed instability. This allows us to study the lowest energy phase and finally to see if it would be possible to induce ferroelectricity in the ground state through the strain. Here are my tools. I use Ab-initio code, and for exchange correlation energy, I use GGA PBS Sol. But for some calculations, I checked the result with LDA also. Here are the different phase transition of these two materials. You can see that indeed the two compounds present the same phase transition, even if in strontium zirconium some study put CMCM phase in place of the EMMA phase. In our case, our study has shown that it is the EMMA phase that it is energetically more stable than the CMCM phase, but the ground state stay the same. Here are now our relaxed cubic parameters in these two compounds and in two others for comparison. The bond effective charge of B and some O atom are strongly anomalous. These anomalous bond effective charge are known as a common feature of perovskite compound and were related to dynamical transfer of charge between the BD and O2P orbitals. The bond effective charge of strontium hafnium are in fact closer to those of strontium zirconium than those of titanate. The calculated optical dielectric constant is near to that for strontium zirconium, but it is smaller than for titanate. Within our calculations, strontium hafnium oxide is described as a good insulator with an indirect band gap between R and gamma point, which is closer to that of strontium zirconium, but wider than that of strontium titanate. So let's report now the phonon dispersion curves of strontium hafnium oxide. Negative value in the graph correspond to imaginary phonon frequencies and are related to unstable modes. So by condensing this unstable mode, it is theoretically possible to find the possible intermediate phase and the stable phase of a compound. We have 4 unstable modes. M3 and R3 correspond to the rotation of oxygen octaedra in phase and out of phase. At gamma point, we get the polar mode, and at M point in strontium zirconium, we observe a smaller antipolar mode. You can see here that the phonon dispersion curves of strontium hafnium are similar to those of strontium zirconium, particularly for FD mode. The only important difference is the amplitude of the instability that are larger in strontium zirconium than in strontium hafnium, especially for the gamma point here. For strontium zirconium, we get 87 negative value, but for strontium hafnium, we get 49 negative value. So let's when we condense now only the FD instability with various combination. As you know, we have in phase and out of phase rotation. You can see that in phase rotation is more favorable when you condense only in one direction than in 2 and 3 direction. But the out of phase rotation is more favorable when you condense in 2 direction than in 1 and 3 direction. Even by adding the ferroelectric motion in this 3 direction distortion, whatever the functional used, we still do not observe an additional energy. You can compare, you see this, here you have 2 direction out of phase rotation, and here we have 2 direction out of phase rotation plus ferroelectricity, but the energy stays the same. So, similar to what was found in strontium zirconium, the CMCM and the EMMA phases are similar internal energy, with only the difference of 10 millielectron volt to the advantage of the EMMA phase. The EMM phase is not yet observed experimentally, but it seems to be more favorable in strontium hafnium than that CMCM experimentally reported. So when you combine now the one in phase rotation and the 2 out of phase rotation, we obtain the PNMA phase, which is more stable as antiferrodistortive instability in this compound. So let's finally see the behavior of these 2 materials when we condense only the ferroelectric instability. You see here that it is the tetragonal P4 MM, which is the most energetically stable compared to the other in both compound. And in both cases, we see a sizable contribution of the strain reduction in the stabilization of this stable ferroelectric phase state with a large relative energy gain. Another striking fact is that when we calculate the atom eigen displacement of the polar instability, when we consider the titanate perovskite here in the cubic phase, the eigen displacement vector of the polar instability is dominated by opposite displacement of B and O atom, while for FD perovskite here, hafnate and zirconate, the B and O displacement contribution become smaller, and at the gamma polar instability, and the B atoms here appear to move now against, not against, but with the oxygen atom. To see the possibility to induce ferroelectricity in PNMI ground state in both compounds, for strontium zirconate, we succeed to induce ferroelectricity in PNMI ground state. So we get PMC21, but in strontium hafnium, this compound prefer to stay in the PNMA phase. Contrary to strontium zirconium, it is not possible to induce ferroelectric PNMA ground state in this compound. And here we have the conclusion. So thank you very much.
Thank you, Amisi. And we have questions? I have one question. Do you have, there are temperature-induced transitions, I believe, to the cubic phase?
Renata?
Yes?
He's going to answer in the chat.
Okay.
Yeah.
All right. Should we wait for discussion later?
Well, he's able to take questions now. So I would say if people have a question, they could type it into the chat.
Okay.
And you can also ask your question and he will type his response in the chat. So let's take 2 or 3 questions right now since his connection is good for chatting.
Okay. So my question, Amisi, these compounds have different temperature-induced transition. Probably to the cubic phase at high temperatures, but different temperatures. Are you able to tell us the transition temperature to the cubic phase for these compounds? Michelle Cote is asking for some details of your calculation. Maybe you can type your answer. Maybe it's not a short answer. Let's give a few more seconds. But then I think we should move on because if he's not responding in the chat.
Gamaches, can you also just type your question in the chat? Then everybody can read your question.
My question, you mean?
Okay, okay.
Gamaches, yeah.
Yep, I'll do that.
Thank you. So Safari will wait for your typed response, and then I believe that Sarah's ready after a question or 2.
Okay.
Oh, Sara is in now. Okay.
So
are you chatting with her, Amy?
I'm not. Sinead is, but Safari has posted his answer on the K point, Michelle's question, in the chat. So Safari says that the K point depends on the volume that you use.
Okay.
Yeah, we're going to create a breakout room later on.
Yeah,
Safari
I agree.
Will be,
I agree.
Yeah, Safari will be in one of the rooms and we can ask. Yeah. So if Sarah is ready now,
okay.
we go to Sarah. Then after that, go to Ridwan.
Right. Sarah, welcome.
Okay.
Yes,
sorry for the
we can hear you.
interruption.
Yes, we can hear you well. Yes.
Yeah. Okay.
So I don't have the, let me see. I don't have the title of your presentation, but please start. You're welcome.
Okay.
Share your screen, please.
Glad you're here now.
Yeah, thank you.
I am going to time.
Okay, now can you see my screen?
Yes.
Okay. Yes, but it will make it full screen, no?
Yeah.
Yeah, if you go to presentation, maybe.
Okay, now you can see it now.
Perfect.
Okay. Can I start now?
Yes, absolutely.
Please go ahead. Please go ahead.
Okay. Hello, everyone. I'm sorry for the delay and interruptions. Okay, my name is Sara Abass from University of Khartoum. I'm going to present here as a part of my PhD work that is done in the collaboration with the University of Khartoum and International Center for Theoretical Physics. Okay, the title of my talk is the structures and electronic properties of hydrogen and sodium titanate. In the introduction, why do you need for renewable energy? Because securing safe and sustainable energy is a key challenge at the present time. And this is because the traditional source of energy, such as fossil fuel, are finite and cause environmental problems. And other solutions, such as the solar energy, have their problem. And solar energy is appeared to be the most safe and abundant source of energy to be used in the future. And presently, the most effective way to use the solar energy is in the photovoltaic cell, where the solar radiation is directly converted to the electricity. But this depends on the availability of the solar radiation. A possible solution using the solar energy to produce a chemical fuel is known as a photochemical use. And one important of the photochemical method is a photocatalyst. In a photocatalyst application, the standard material of choice is titanium, for its wide range and low toxicity, high stability, and wide activity. Among titanium polymers, and it is achieved to have the highest efficiency for photocatalyst application, and also have a band gap around 3 electron volt and absorption in the ultraviolet range, but not in the visible range. And doping titanium with hydrogen was found to improve as an absorption in the visible range and activity. The role of hydrogen in the stability of hydrogen doped and titanium oxide and hence photoabsorption is still not clear. It is great interest to study at atomistic level the interactions of titanium with hydrogen by investigating the properties of hydrogen-rich stoichiometric crystalline titanium oxide compound, such as hydrogen titanium and its isostructure sodium titanate. The aim of this work is to perform a density function theory on hydrogen titanate and sodium titanate with the following objective: to optimize the crystal structure and to study the thermodynamic stability of the titanates with respect to titanium, and to investigate the electronic structures of the two titanate related to the titanium, and to investigate the effect of point defect on their electronic structure. And the methodology, we use quantum espresso package plus DFT. And for ultrasoft and for pseudopotential, we use ultrasoft pseudopotential and plane wave cutoff of 30 red pill and 360 red pill for wave functions and charge density. And the exchange correlation function was described by using generalized gradient approximation. And for K point, we use 3 by 1 K point. And now this here is our structure, is the structure of hydrogen titanate and sodium titanate. The both structure has a monoclinic structure with a space group P21 meter. And the experimental band gap for hydrogen titanate is 3.36 electron volt and 3.46 electron volt for sodium titanate. Okay, now it's here. We are going to look at the configuration of hydrogen titanate, because in the experimentally, the hydrogen, the position of hydrogen were not well determined due to the weak interactions in the comparison to the other elements. And our calculation shows that half of the hydrogen form water and the other remain in OH group. And in this figure, H5, this figure indicates the stable configuration with a single cell. And then we double this stable structure in Y direction, and we got this structure. And our calculation confirms that the stable structure for hydrogen has a double cell, and the single cell lie higher in the energy by 0.14 electron volt. And here in this table, we try to put all the configuration for all the lattice parameters for all the configurations. This H1, H2 is referred to all the configurations of hydrogen. Okay, and here we compare our crystal parameter for two titanates with experimental work and other theoretical work. And our calculation confirmed that our data, it is less than the experimental data by less than 1% in all cases. And also we check the stability of this structure by applying the strain in the unit cell. And then we calculate the total energy. And this data were fitted by using a quadratic polynomial, and then the relative elastic constant was accurated from the coefficients at the quadratic term in their equation. And here we table all the elastic constant in all the cell for hydrogen titanate and for sodium titanate, and in the unit of gigapascal. And also we study the electronic structure of hydrogen titanate and sodium titanate. And the calculated band gap we obtained it is 2.96 electron volt for hydrogen titanate and 3.13 electron volt for sodium titanate. And these gaps are smaller than the gap of the experimental work. But they are in the same range of the titania. And from those two structures, we can see that is the oxygen 2b state are dominant at the bottom of the conduction band, and the contribution of hydrogen and sodium are neglected. And the comparison of conduction band and valence band is similar to that of titania. And this is support to the experimental observation that the titanates have similar function as titania for solar cell and photocatalyst. And after that, we introduce a defect, okay? And the electronic and optical properties of oxide are often determined by presence of the defect, either intrinsic or introducing defect. And here we have investigated that the defect of hydrogen titanate and sodium titanate, including hydrogen vacancy, sodium vacancy, and OH vacancy, and sodium oxide vacancy. And we compare it with other theoretical work. And from this table, we can see that the hydrogen vacancy and sodium vacancy have the lowest formation energy. And also we take the thermodynamically stability. The chemical potential of the relevant species have used to calculate free energy in the contents of the Ab-initio thermodynamically. And we know that at low chemical potential, hydrogen vacancies become thermodynamically more stable than the perfect structure. And this is happened at delta mu equal -3 electron volt. And the system without hydrogen is more stable than the system with hydrogen. And at that temperature, 100 Kelvin, the system can absorb hydrogen. And also at low chemical potential, the hydrogen vacancies become thermodynamically more stable than that of the perfect crystal. Also, we study the effect of a defect on electronic and structure. And we've done that the defects have important effect on electronic structure in both cases. And the Fermi level move below to the top of the valence band, leading the whole being a majority carrier, a reason of the defect. And from this calculation, we expect this compound to either become an intrinsically B-type semiconductor. And after that, we open a vacuum in Y direction, about 20 angstrom, and the structure will relax it, and then we calculate the surface energy by using this formula. And we obtain that the surface energy for hydrogen titanate has 17 mega electron volts, and for sodium titanate is 26 mega electron volt per angstrom square. And this means two compounds have low surface energy
promoting exfoliation of the bulk and the formation of 2D material and nanotube. And in the conclusion, the crystal structure of hydrogen titanate has a double cell with respect to the sodium titanate. And the band gap of sodium titanate is slightly larger than that the gap of hydrogen titanate by 0.17. And both are in the range of titanium. And the two titanate display ionic vacancy with a relatively low formation energy, and hence lead to the appearance of empty state at the top of the valence band. And the defect with the lowest formation energy are the hydrogen and sodium vacancies. And they are likely to behave as a B-type semiconductor. And oxygen vacancy formation is supported with respect to the titanium dioxide. And from the surface energy, we found that it is easy to exfoliate this material in the formation of 2D material and nanotube. At the end, I would like to special my post-supervisor, Dr. Nicola Siriani from ICTB, and Prof. Hisham Mudakallah from Sultan Gabos, and also Quantum Express. And also, I would like to thank Sinead for giving me this chance to give a talk. Okay, thank you, everyone.
Thank you, Sara. Thank you so much. Thank you.
Okay.
Do we have questions?
Okay.
Hello?
Hello?
Questions for Sara?
Okay.
We have questions in the chat, and also Gamachis has a question.
Okay, the questions are moved fast in the chat.
Okay, now I can
Okay,
open
so
the chat.
I see a question from Lynette. Why didn't you consider post DFT?
Yes, I saw the question.
Okay, yeah. So Sarah, go ahead, and can you answer Lynette's question?
Hello, can you hear me?
Yes.
Okay, so thank you for the nice presentation, Sara, but I have one or two questions. I know titanium oxide is in monoclinic and the tetragonal crystal structure that we can find, right? The system you are focusing with the hydrogen case and the sodium case is found to be in monoclinic, right?
Yes, it's monoclinic, yes.
But you compare with the tetragonal titanium dioxide crystal structure. Why?
I compared what? I compared the post structure. Because the both of them, they have the same group. Yes.
Yeah, so you use
and also when we dope with sodium and hydrogen, the materials become like have the black hydrogenated, and this means you can use it for the solar cell. Yeah, because we are looking for the material we can use it for the energy application. Example for a solar cell, yeah. And those material by this what we got, it is easy to use it for a solar cell and for photocatalysts.
Okay, thank you. The second question is like from your PDOS calculation.
Yes.
I can see that there is some fluctuation of in the conduction band and in the valence band. In some cases, the d orbital is dominating. In another case, the oxygen p orbital is dominating. Why this is going on?
No, because we are choosing a different oxygen atom. Here, what we will see in the figure, we are choosing the different oxygen atom, but we found all the oxygen atoms that are dominant at the conduction band.
But yeah, I can see. If you see this one, the red one.
The red one.
Yeah, the red one is 3D, right? Titanium 3D.
The titanium, yeah, titanium 3D.
In the conduction band, right?
Yes, yeah.
It is dominating here.
Yeah.
When you go back to the valence band.
To what?
In the valence band, it's not, titanium is not dominating.
Sorry, I cannot hear you well. What you said?
In the conduction band, in the valence band.
Okay. That means the contribution of the titanium, it is
not
small.
dominating. Yeah, in principle, it should be uniform, right?
Yeah.
Why? But it is not like that. Maybe say something.
But if you compare it to the other oxygen, this I think you will find it is less contribution.
Yeah. The oxygen 2p is dominating in that in the balance one, right?
What?
The green one is dominating. Oxygen 2p orbital is dominating the system.
Yes.
Right?
Yes.
Whereas in the conduction band, the titanium 3D is dominating. Can you see that one? The red one. Titanium is dominating. Yeah, in principle, it should be uniform, right? In the conduction band and the valence band, the orbital which dominates the system should be most likely. Sometimes we it should be uniform. So I can see some delocalization, right? Orbital delocalization.
Yes.
So I think the oxygen 3D is 3D transitional material, right? Titanium.
What you said? The last one?
Titanium is 3D. It is transitional metal, 3D, right?
Yes, it is here, yeah?
Yeah, you can see some delocalization. So I think it's good to consider, for example, like how to localize this one. That is the one where I wanted to say. Yeah.
Oh, is it okay for me to interrupt? I'm sorry. So we would you like to take more questions, or shall we continue?
Yeah, perhaps we should leave this discussion for later.
Okay.
Okay.
Thank you, Sara. Thank you very much.
Okay, thank you.
The next speaker that we are going to introduce now is Ridwan Agbaoye. Are you ready, Ridwan? Ready?
Yes, I'm here. I would like to share my screen.
Wonderful. Thank you. Thank you, Sara.
Okay, thank you. Thank you.
I think you should stop sharing your screen now. Okay. Yeah. Thank you.
Can you see my screen?
Yes, everything is fine.
Yes, we can see.
Yeah, great. Good afternoon from Nigeria. I am Agbaoye Ridwan Olamide. I am from the Federal College of Dental Technology and Therapy in Enugu, Nigeria. So I would like to share with us some of our results in the research we've done for a while now. We're interested in searching for a highly efficient perovskite solar cell absorber. In Africa, one of our major challenges is that we have poor access to power supply, and some of our power generating stations work on fossil fuel, which is not very good for our environment. So my research is based on looking at perovskite solar cell and see if we can model materials that will be very good as solar cell absorber and that can rival silicon, which is the existing materials that is used for solar cell. So I would introduce perovskite. Perovskite is a large family of material with a general formula ABX3 for the inorganic perovskite, where A is a monovalent cation, B is a divalent cation, and X is an halide. And also we have a double perovskite that has a general formula H2B prime, B prime X6. And A also here is a monovalent cation, B prime and B prime are divalent cation, and X are halides. So this general formula gives us the opportunity to match different elements that agree with these configurations, and we have thousands of perovskite materials. So this is a limitless opportunity for us to search the periodic table and see if we can get materials that can do very well and see if we can generate solar cell, generate power from solar cell and power most part of Africa. In our previous research, we have worked on inorganic perovskites, cesium cadmium chloride. We also worked on organic inorganic perovskite, where the A site is changed to an organic cation, and here we have methyl ammonium lead iodide. And also we worked with the double perovskite, that is cesium, bismuth, silver chloride. Then the structure of perovskite, experimental studies have showed that for methyl ammonium diiodide, we have three basic phases. The first one is the cubic or the pseudocubic phase that exists at high temperature. The second one is the tetragonal structure that exists at medium temperature, and at low temperature, we have the orthorhombic structure. And as theorists, we would like to work with the ground state of this material. So we decided to optimize the volume of this material with energy. So here we have the volume optimization of these three phases in order for us to know which one has the ground state of the material. And in this work in 2020 for methyl ammonium diiodide, we are able to establish that cubic crystal structure is the ground state, has minimum energy for the three structures of orthorhombic, cubic, and tetragonal crystal structure that we considered. Recently, we also attempted the same thing for tetramethyl ammonium diiodide to see what value we can get from it. Methyl ammonium diiodide has been worked on extensively, and it has been able to generate experimental efficiency, which could rival with that of silicon. But here we want to see what we can get from tetramethyl ammonium diiodide. Some of the demerits of methyl ammonium diiodide is that it has stability issues, and the lead could be toxic, and a handful of other issues. But in tetramethyl ammonium diiodide, I think previous work has shown that the stability issue is minimized, although we still have lead which could be toxic, but we have a better stable material in this case. So we want to see what we can get from this material and see if it could be better or it could have the same experimental efficiency as that of methyl ammonium diiodide. Similarly, tetramethyl ammonium diiodide also has a different structure. It has the cubic structure, the hexagonal structure, and the tetragonal structure. The cubic structure at high temperature, the tetragonal structure at 298 Kelvin, and the hexagonal structure at low temperature. Then we looked at the band structure of these materials, and having established that DFT underestimates band gap of materials, we tend to look at the using GW method to determine our band gap. So we have GW here trying to correct the band gap of this material. Then also we introduce spin-orbit coupling because of heavy metal in lead that is in this material. And the spin-orbit coupling is known to reduce band gap and cause band splitting. And of course, GW method is also known to increase band gap of the material. So we tend to achieve a correct band gap by reducing the band gap using spin-orbit coupling and increasing the band gap using GW. And we hope we are able to achieve the experimental band gap of the system. So here in the table, we did a lot of work, and this is for ammonium diiodide. We're also trying to see what difference we get from ammonium instead of tetramethyl ammonium diiodide. So here we use PBE sol functional. Also, we use van der Waals correction, and we're able to achieve a band gap of 2.23 electron volts as the DFT band gap. So when we use spin-orbit coupling, we realize that the band gap reduced to 1.47 electron volts. And when also we use GW on the same material without spin-orbit coupling this time, we are able to achieve a band gap of 3.25 electron volts, which is higher than the band gap recorded by previous work, which is 2.44 electron volts. But at the end of the day, when we did GW calculation with PBE functional, with spin-orbit coupling, we are able to achieve a band gap of 2.28 electron volts, which is similar, which is closer to the experimental work that is done by previous researcher, getting a band gap of 2.67 electron volts. So here we are able to, we did not achieve the exact experimental gap, but we have a better gap compared to what DFT is offering. without spin-orbit coupling and without GW, and compared to what GW alone is doing. So here we are trying to use GW and also merge with spin-orbit coupling such that we are able to achieve a very good band gap. So here we have the band structure of methylammonium of ammonium lead iodide for DFT and GW structure. And then we are also interested in looking at the absorption spectra of perovskite material. And for ammonium lead iodide, we are able to do the optical absorption spectra. And here we have the result of absorbance using 4 different methods. The first method is for us to use TDDFT with spin-orbit coupling. The second method is to use beta-sepeta equation without spin-orbit coupling. The third is to use only TDDFT without spin-orbit coupling. And the fourth is for us to use beta-sepeta equation with spin-orbit coupling. Then we compare the result of the absorbance with 2 different experimental results. That is in work in 2021. And we realized that the beta-sepeta method has similar results compared to the experimental value. But when the beta-sepeta equation was used with spin-orbit coupling, it has much more better results compared to ordinary BSC. So here we are able to establish that beta-sepeta equation works better than TDDFT, while using spin-orbit coupling on beta-sepeta equation, we're able to get much more result that is closer to the experimental value. So in 2020, we also looked at the fact that since lead is said to be toxic, we can dope lead with magnesium. So we did that with a lot of configurations where we have lead to be 25%, magnesium 75%, lead 75%, magnesium 25%, and we have a whole unit cell of methylammonium lead iodide, a whole unit cell of methylammonium magnesium iodide. So with that, we're able to check the absorption spectra, and here we were using TDDFT, and also we are able to realize that the peaks on the experimental results are reproduced by TDDFT for methylammonium lead iodide, which we can find the references, and also we're able to do that the same thing for refractive index. We're able to reproduce the peaks and have a very good result with absorption coefficients. These results, these calculations were carried out for GW with the Yambo code, while the DFT calculations were carried out with Quantum Espresso. In the next phase of our research, we hope to do high throughput screening of perovskite materials. We hope to search the periodic table and take all the eligible anions and cations and see how we can mix them together with several organic cations. We are interested in dimethylammonium. We are interested in methylammonium, tetramethylammonium, ammonium, and so on. So we're interested in a lot of cations and see how we can mix them together to have results that will be exciting. And then we tend to look for material for solar cell absorber. The first thing we look at is the DFT band gap between 0.5 electron volts to 2 electron volts. Also, we do GW band gap to select material that best fits for solar cell absorption. We are looking at also at materials with absorption coefficients that is greater than 10 raised to power 5, and a whole lot of properties we tend to that will be useful for our solar cell material. So basically, this is a summary of what we've been doing for a while, and we hope going forward, the high throughput screening will lead us to more exciting research areas, and we hope to be able to get results that would see how would leverage on the efficiency and also find a good cost, because cost is also very important when we talk about using these things in Africa. So basically, this is my presentation. Thank you for listening. I would also like to thank Sinead specifically, and also like to thank the SESMA group for introducing me to this very wonderful subject area. And since then, I have been trying to see if we can get good perovskite materials that will be good for solar cell absorption. Thank you.
Thank you so much, Ridwan. The talk went very well. We could hear well. So do we have questions here?
We have some questions in the chat. We have one from Michelle Cote.
Okay.
Michelle, can you ask your questions or should I?
Yes, I can ask my questions. It's concerning at the beginning of your talk, you presented the energy versus volume result. And I was a bit confused because for the different phases, that the minimum volume was at really different location. And I would like to know if the volumes are expressed per unit cell or per unit formula.
Okay. Here.
Slide number 3.
I think I am on that slide.
It would be slide number 3.
I think this particular one, can you hear me?
I can hear you, but I don't.
Yes, it's slide number 3.
Okay, I think I am on the slide.
No.
Oh, sorry.
Yes, that's the slide.
Okay, yes. So here we are looking at the energy with respect to the volume, and the volume is far apart in the first graph here because the cubic structure is smaller than the orthorhombic and the tetragonal structure. The cubic has the same value in XYZ, which is about 5 point something Armstrong, while that of the orthorhombic and tetragonal is quite larger. It's just that we are looking at the unit cell of both material, and obviously orthorhombic is larger than cubic, and also tetragonal is larger than cubic. So that is why we have them far apart.
Okay. All right. Yes, it's not expressed in formula unit. Do we have more questions? Okay. Ridwan, thank you so much. We'll talk more in the panel session later, okay?
Okay, so, thank you very much.
Thank you. We are ready for the next speaker, which will be Yuan Ping. Yuan, can you start sharing your screen?
Sure. Can you hear me?
Yes, very well.
Okay. So I will get started. Can I start now?
Yes.
So this is okay. This is Yuan Ping, coming from University of California, Santa Cruz. Today I will introduce our very recent work on ab-initio spin dynamics in solids. Thank you for the invitation. So first, a brief overview of the projects in our group. So we are a serial computational material science group. In our group, we develop methods. In my early years, I worked with my coworkers on solving the better speeder equation without empty states. And this is an important method to treat the solids, including electron-hole interactions. And later on, I worked on exciton recombination from radiative and non-radiative processes. And today, I mostly focus on the discussion on the quantum dynamics for open systems, which are useful to treat spin dynamics. In terms of applications, we have the corresponding applications on spin qubits and spin transport, polarionic transport, which is useful for solar water splitting and photochemistry in heterogeneous system. A lot of times, theory development is accompanied or motivated by applications. And our group bridged the condensed matter physics community with the physical chemistry to solve complex material problems. So the one big motivation for the research is for quantum information science, where as a material theorists that would like to design materials for qubits, in particular spin qubits in quantum sensing and quantum computing, where you need long spin coherence, efficient readout, and quantum transaction, which can help connect the different qubits. So what are the specific material criteria if you want to have a candidate material which can be used as a spin qubit? Here are a list of properties. For example, they have to have deep defect levels. This level will be separated from the bulk, and bright optical transitions, which can be read out by photon, and high spin state and large zero field splitting. This is necessary. For example, for NV center in diamond, where we are going to operate the spin state, and high quantum efficiency and PL contrast. This is necessary if we want to read out information from the qubit. And last is the long spin relaxation and coherence time. This is necessary if you want to have reliable operation of your qubit for a long time. Correspondingly, we have been computing these property developing methods for 2D materials. The reason we investigated defects as qubit in 2D materials motivated by quite a few experimental work for HBM. First, we developed methods to deal with the charge defect correction. This is because for the charge defect in 2D material, the convergence is problematic. And in this work, we developed the methods where we do not need any supercell extrapolation to converge the calculation. And then we apply the GWBSC calculation to compute the defect levels and the optical transition, including electron-hole interaction. And this is also necessary because they have very large electron-hole interaction in material, for example, a thin layer HBM. At the end, with the electronic structure and optical property, we look at the radiative and non-radiative recombination. As this example show, we designed dye vacancy with MO defect in HBM. And more importantly, we also computed intersystem crossing between triplet and singlet, and it's a necessary step if you want to initialize the qubit. And we can use all these rates to predict the PL contrast, which is basically related to the readout efficiency. And we can also look at how the lifetime respond to strain, as this example of nitrogen vacancy. So more details of the work you can find in the following paper. So one of the important challenge in this field is the decoherence of encoded information, which we will lose information when the state interact with the environment. So what are the specific mechanism for spin qubit? At a very low temperature, decoherence may come from fluctuated magnetic field. And this is also under large B field due to the nuclear spin interaction. At a finite temperature, other effects may be important. For example, phonons, impurities, electron interactions through spin-orbit coupling, which will relate it to spin. And to deal with this interaction in a general way, we look at the open quantum dynamics, including the decoherence pathway, which we can also study coupled spin and carrier dynamics for solids, which is within the framework as I show here. And in the open quantum dynamics, you deal with the environment as a Abass. If you treat it at a level neglecting the correlation effect, and you can derive the Lindblad dynamics, and go down the ladder if you treat your system at quasi-equilibrium, then you can derive the generalized Fermi's golden rule. And at the end, if you treat it semi-classically, you recover the Boltzmann equation, where your density matrix become a diagonal occupation number. So we do the time evolution of density matrix, which included the coherent part, where you have the light matter interaction, a magnetic field, the electric field, and scattering part, including the scattering due to electron-electron, electron impurity, and electron phonon with a spin-orbit coupling. So the introduced states can come from DFT, or you can use the higher level theory. And we implemented this in the interaction picture, where we're going to put the electron correlation in the H0, basically static. And we computed the observable by taking the trace of density matrix with a spin operator or carrier. What's the advantage? We can simulate a long time, for example, over nanosecond or microsecond. This is necessary if you look at the spin. And this is adequate for spin dynamics because we use the density matrix instead of diagonal occupation number. And we can treat it in out of equilibrium state because we are doing explicit time evolution. So this is overall of the look of the computational scheme. We start with the DFT simulation with the spin-orbit coupling with the coarse mesh, where you can get the eigenstates, the phonons, and electron phonon matrix element. And electron phonon matrix element you can get from QuantExpresso, or use another code from our collaborator GDFTX. And then you do the one-year fitting, you can extrapolate to very fine mesh, which is necessary for our implementation to converge the K and Q points. At the end, we do the density matrix dynamics, where you have the scattering matrix needs to be computed. Then you do the time evolution of rho, and then you can look at your observables. The most time-consuming part is how to compute the scattering. There, as I show here, for each part, we all deal with from first principle with a certain level approximation. For the electron phonon part, it's rather established. We include also self-consistency. For the electron impurity, we treat the ionized impurity with a screen Coulomb potential, which deal with the long-range part more correctly. And for the neutral defect, we use the supercell DFT potential. For electron-electron interaction, we include the screen Coulomb potential with RP dielectric function. We benchmark against the GW self-energy at finite temperature. So at the end, I'll show you a few examples. First is the example of spin lifetime of silicon and ion, which these two systems has invariant symmetry characterized by low effect mechanism. And compare with experiment in wide temperature range. We also give the carrier lifetime, can show they are much lower than the spin. We also show for system with invariant symmetry, because broken invariant symmetry will break the Coulomb degeneracy between the up and down spin, which will create internal magnetic field to cause spin precession. And this will also scatter with other phonons and environment. So we show you example of MOS2 and gallium nitride. And I want to note the example I show here are more for intrinsic system where we generate a spin balance by a circular polarized light or magnetic perturbation. And I'll also compare it well with experiment. And more importantly, we show example of gallium arsenide spin and carrier dynamics with initialized by circular powered pump, and we probe the system. You can look with a shorter range, time is mostly carrier relaxation with fast oscillation. In the long range time, you can see there's an exponential decay, which you can extract the spin lifetime. There we show you the Kerr rotation angle and the spin expectation value basically overlapped, which give you the same value as expected by the Kerr measurement. And we can also look at what kind of contribution is the most important. For example, for the spin lifetime, the electron phonon is most important in the higher temperature, and electron-electron is more important in the lower temperature. And this is very different from the carrier lifetime. For example, the black is also include the total, the electron impurity is important for wet range until the electron phonon heating at a high temperature become mostly important at 300 K. So this basically where our skin can tell you what mechanism is important at a different condition, and we can predict reliably the spin and carrier relaxation. I'll go to the end of the talk. We developed this method for open quantum system, which should be a general method to study decoherence. And we also introduced our work on defects in 2D material for its optical property and excited state dynamics, which is important for looking at the readout of the qubit. Okay, I would like to thank to my funding agency and my collaborators. Thank you for your attention.
Oh, thank you very much. Lovely talk. Very nice talk. Can we, do we have questions here? Okay. It's 10:38 in the morning now. And we were supposed to start the breakout rooms at 10:50. Oh, this is New York time. And we are supposed to start with the breakout rooms at 10:50, and we didn't have a break this morning. So I suggest we break now and reconvene at 10:50 in the breakout rooms. They will be open then. I think they are already open, right, Amy?
Not yet, but I can do that now.
Okay, so we'll reconvene at 10:50.
So that will be in about 11 minutes.
Correct.
Okay.
I will talk to you later, Yuan. Okay, in your break.
Thank you.
Thank you.
Hello, Renata, Sinead, can you hear me?
Hi, Richard. Yeah, I can hear you.
Hi, good. You're doing a marvelous job, and Renata too. Thank you. And Omololu too, of course.
Richard, I'm going to run and get some tea. I haven't had any caffeine this morning, so I'll be back in 5 minutes, okay?
Fine. Thank you. So I'm in a noisy place, and I'm really delighted that I'm not responsible today.
Richard, we will start the breakout rooms in 8 minutes.
Okay.
I'm on break right now.
It's perfect.
Yeah.
Oh yeah, I've been listening all the time.
Hello, Richard.
Hello, who is that?
Hello, this is Gamachis. I am
Oh
very
yeah.
happy.
Okay, glad to see you.
Oh, Richard, can you hear Amy?
Yes, so very well.
Okay, I put a message in the chat, and I'd like to, whoever's still around, to remind everybody to just check their audio settings in the chat. In the bottom left of your Zoom screen, in your audio settings, you just click that up arrow and click audio settings. And then on the left-hand column, you'll get to audio. And it says suppress background noise. Do you see that?
No, I don't see that.
Okay, so Renata, are you able to, with your little microphone where you would mute or unmute yourself? Do you see there's
Yes.
a little up arrow?
Yeah.
And then at the bottom of that, it says audio settings.
Right.
Okay.
And then once you select audio settings, does it pop up the Zoom, the white Zoom picture?
Yes.
Yes. And then you see it says suppress background noise.
Suppress background, right.
Okay.
Auto.
So mine's on auto.
Yeah.
But I think for people who might be in a noisy location, you might go ahead and click high. Yes. Let me share my screen so people can see
Oh, what a good idea.
what
I
I'm
didn't know
talking
this.
about. Okay, yes. So you first go to your little microphone audio settings, and then this within there. So if you're in a noisier location, I think high might be better.
Yep.
Okay. And that's just for everybody.
Okay,
Okay.
I'm trying it.
All right.
Audio settings. Speaker.
I'm going to stop the